Okay, so this is a real super quick thing on phylogenetic trees and cladograms, and these are basically common sense. So right here I have two different, I don't know, charts, and this one that kind of starts at this point and goes, you have a straight line with branches coming off. This is the phylogenetic tree. Phylogenetic tree. And the one that kind of has got more squares squared off, this is a cladogram, and they're both very similar. They're just different ways of showing relationships. So cladograms, it has one job, and its one job is to show relationships. So you would take a whole bunch of evidence, maybe it would be DNA evidence, looking at DNA for a certain protein and seeing which ones have ATGC, nitrogen-based sequences, which are more alike and which ones are less alike, and that would show you which were more or less closely related to each other. A phylogenetic tree like this one, right, it shows relationships, but it also shows change over time. Okay, and we'll come to that in a second. What they both have in common is this point here and this point here, where they start, because they both start at the common ancestor. Okay, so the beginning of the line on each of them represents a common ancestor from which everything else has come. Now, phylogenetic trees show change over time, and so you would think, and it makes perfect sense, that when you start here, this is the oldest part and this is the newest. As you go down this line, right, as you go from oldest to newest, like that. Okay, now let me give you another thing. So let's say we're talking about fossils, right? You know, if you go to a beach, sometimes you see cliffs. Okay, and if you drag yourself back to when you were in middle school and we talked about the rock cycle and all that good stuff, rocks at the bottom of a cliff are the oldest, rocks at the top of the cliff, right, are the newest. Okay, so if I find a fossil down here, it's older than if I find a fossil at the top. I want you to bear that in mind in a minute. So what this says is we start with our common ancestor and along we go, and then we off from the changes happen to the common ancestor, and the first thing to branch off is C. That would mean C of all of these things here is more closely related to the common ancestor. You might find C way down here in fossils at the bottom of the cliff. The next one as we come along is B. You would find B higher up the cliff because you would find it in rocks that were younger than the rocks that you find C in. And then obviously at the end here, you may find A all the way up here at the top. Okay? So this shows by looking at how they branch off what order they appeared in something like a fossil record. Now, if I took another example, and these were like I said, like DNA. So you start off at this point with the common ancestor, and the first thing to branch off was C, right? So C came first, and then you come along here to A, and A and B branched off of a common ancestor. So there'd be like another common ancestor just for these two. But by these two coming off the same branch, one thing that I do know is that these two, because they're coming off the same point here, these two are more related to each other than they are to C, because C comes off another branch. And that's, that's the basic thing. This is common sense. Like I said, I do not want to overcomplicate it. I do want to show you, this is an actual example of a phylogenetic tree. And sometimes you will have time frames, like millions of years, how many millions of years ago these represent. But when you look here at this one, right, so again, starting at the bottom, this is our common ancestor, okay, Ancestor. And the first thing you can see is you've got a type of organism called a hagfish. Hagfish were part of a group called the jawless fish. Basically, their mouth was a hole that they couldn't really open or close, okay? And so as they swim around, food and stuff happens to go into their mouth and they can absorb it into their digestive tract. So these were the very original kind of fish type things, were jawless fish. And then you'll see along here, we have a little milestone here because jaws developed. And that gives rise to the type of fish like perch, like what we know about. And these are the jawless fish. Right? So if you were looking at fossils in a cliff face, you would find jawless fish at the bottom. A bit higher up the cliff, you would find jawfish. Now, these have to live underwater. And the reason for that is we have yet to develop lungs. So when lungs developed, right, that meant that we could have organisms that could start to colonize the land. And that's where the amphibians come about, like frogs and newts and toads and stuff like that, and salamanders. Now, the interesting thing about amphibians is when you look at when they reproduce, they have to reproduce in water. Think about frog spawn. Like you have the female frog lays eggs in the water, the male frog lays sperm in the water, and you hope the sperm and the eggs meet, and then that gives rise to tadpoles, which have to stay in the water and have a modified form of gill until their lungs have developed sufficiently that they can get on the land. So amphibians still have to, they still got that connection to the water because they have to reproduce in it. Once the amphibians had colonized the land, the next thing we find in fossil records are claws and nails. And that gives rise to animals which can live on land all the time. And there we get the reptiles. But reptiles, for reproduction, they still require their offspring to develop in a watery environment, which is why they have eggs that have a liquid, a water type fluid in them. When the reptile has fully developed, it breaks the eggshell, the leathery eggshell, and it's on its own. It's good to go. It is basically an adult at that point. It might be small, may need to grow more, but it's still good to go. Coming along after we've got our reptiles develop feathers. And of course, if it's got feathers, it's a bird. Birds still require their offspring to develop in a watery environment, which is why they lay eggs. But their offspring, and they develop outside of the parent. But unlike reptiles, when baby birds are born, they still require parental support. They still require, baby birds get fed by their parents until they're developed, they've got feathers, are fully developed, they can fly, and at that point they leave the nest and they typically never go back. But we have finally got some parenting going on. Following along our timeline, we've now got fur and mammary glands. Mammary glands produce milk, and that gave rise to the mammals. Mammals are the first organisms that the offspring develop internally. We have internal, birds and mammals both have internal fertilization, but mammals, the baby develops inside the mammal, the parent, the mother, until it's ready to be born. But when it's born, it's not anywhere near maturity. And so mammals put a lot of time and energy into raising their offspring, and one way they do that is they produce their own milk for them. Okay, so this shows you changes, key points along the way. We know down here, these are the oldest, right? This is the newest, right? If you were to look at the DNA of this, you would find that chimps share more DNA in common with mice than they do with jawless fish. And jawless fish probably share more DNA with that should not say jawless, that should say jawed. I have to change that. That should say Jawed, jawed fish, right? So this has got a time or a temporal element to it, but it shows you key points. If I found a fossil of an animal with fur way back here, that would tell me that mammals did actually develop much earlier than I thought they would. So it gives you an idea of the sequence of which things develop. And so this is a phylogenetic tree. They're very straightforward. They're just straight common sense for you to kind of look at it and draw your conclusions. But they always, always start with a common ancestor.